mind that 5 and 6, think of them as one big group of information, that is Newton's 3 laws of motion. And if you know how to do Newton's 3 laws of motion, then ideally anyways, you know how to solve all the problems that are in 5 and 6. And of course, as you saw by doing them, there's a lot of detailed steps that go into play, but at least that's the framework, if you will. Likewise, the chapters 7 and 8, I would put that in the category of conservation of energy. And so look at all the energies. If you add them all together at one moment, that's equal to all the energies at another moment. And so last lecture you saw me do a bunch of examples with conservation of energy. So now it's ready to move on. So let's get started here in Chapter 9. My goal here is to introduce Chapter 9 and to get as far as we can into Chapter 9 here today. Then on Monday we'll have the test. That followed then, of course, by the following Wednesday, which will finish up Chapter 9, which then will mean you can go into spring break with quite a bit of time to do Chapter 9. As you'll see, Chapter 9 is a long chapter. It breaks itself really nicely into two sections. I kind of wonder if it shouldn't be broken into two chapters because it is so long. But on the other hand, they do tie together. I would even encourage you over the spring break to look at Chapter 10 because the two longest and to some degree the two hardest, not just because they're long even, but because the material is hard, is this Chapter 9 and Chapter 10. And so I think you will see that. Maybe not here today because we're just going to do the first half of Chapter 9 and you'll see, at least I hope you will see, it's straightforward. Sometimes the algebra gets a little bit long. But when we get to the second half of 9, I think we turn a big corner. And you'll see that when we get there. And things get a lot harder than they have been. All right, well, keeping that in mind, let's me introduce here Chapter 9. And it is titled Linear Momentum. Linear momentum is a word that I think you've come across already in Physics 102. In fact, you've heard me say this a lot this semester. It's worth repeating. This course is about taking your fundamental principles you learned in Physics 102 together with all those properties and principles of mathematics and putting them together, whether on a calculus level or a trig level or an algebraic level, putting those all together and doing harder problems, certainly, than you saw in your 102. So, let's go ahead and define momentum. I'll spell it out first here and just say momentum. The common symbol is after the Latin, so we use a P for the symbol. And it is nothing more than a product of two things we've already dealt with. Now to complete it, I would put a little arrowhead over. And as you know, since Chapter 3, we've been distinguishing is something a scalar or is something a vector. And so notice then that this says mass times velocity, a vector, not mass times speed, mass times velocity. It is a vector. So, of course, it's going to come out to be a vector. I guess in a long form, it would look something like this. I would take the mass of it, and the velocity vector then means that it would have an x component and a y component. You could even argue also a z component. And periodically we have used the 3 dimensions. And maybe this time I'll put it up here now that you're getting a little more advanced in your physical reasoning and your physical pictures. But most of the time, as you have seen, and will continue to see, we will focus on 2 dimensions with the idea that if you could do the 2 dimensions, extending it to the 3rd dimension is usually a natural step. Sometimes a hard natural step, but a straightforward one. So we like to stay focused on the 2, but that means simply that I really have 3 equations up here, right? I have momentum in the x direction is mass times the speed in the x direction. Momentum then has a direction, so the y direction then is mass times the speed in the y direction. And momentum And my P's are kind of looking like capital P's. My kind of hard sometimes on the board to distinguish a capital P from a lowercase p. Maybe this will help. And we'll go back to kindergarten here. And again, just because we did see a P in the last chapter, a capital P, it was for power, and I want to make sure that you're not mixing this P for momentum with the big P for power. And by the time we get to chapter 14, we'll have another P for pressure. But and that'll be a capital P too. There's nothing we can kind of do about that. But again, lowercase p here would look like that. All right. So there is kind of that first step. What is the definition? Going with that first step is then what are the units? The new quantity being momentum, just like the last time the new quantity was energy, which also led then to power. The units. Well, looking at this, I guess I would have mass measured in kilograms. Going beyond that, I would then have the speed measured in meters per second. Maybe it's good news. There's no special name for this. There's not a Newton or a watt that you have to remember. This is it. It is for kind of the history behind science. We kind of give, starting with Newton, any new quantity with Newton and beyond, the name in honor of the scientists in that field. So we have things like a Newton, a joule, a watt. Those you've already seen. Will come up to things like coulombs and amps and volts and some other ones along the way here. But this one predates Newton, so it doesn't have its own formal name, and so that's it. I would say this, though. If you took that quantity and maybe first simplified it as one fraction, and then you multiplied top and bottom by a second, and regrouped things, you would get a Newton times a second. So don't be surprised if you see Newton times a second for also the units of momentum. And a big point I bring that up is next Monday you will do a lab. It'll be your first lab on momentum, and we're going to use the little computer, and one of the things that pops up right away is it shows the units for momentum, and it shows it as a Newton times a second. And in the past I've had students ask about that. And so I want to just answer that now before we get into lab and say, there it is. Okay? I suppose enough said there. Now, why am I introducing this new quantity called momentum? Why is this even useful? That's really what the whole chapter is about here. Watch this for a second. What if I went back to Newton's second law here? What if I wrote acceleration as a derivative of the velocity? What if I take the constant that is out in front of the derivative and put it back inside? I know usually in our math class we take constants and we pull them in front of our derivatives, but what if I put it back inside? So I'd have the derivative first, and then I would have mass times velocity. There's the product, right? Multiplied together. And so a lot of times we see the two multiplied together, mass times velocity. And this is one example of that. And so what I can write then is the net force is really telling me how does the momentum change with time. In fact, maybe that's worth writing. I'll write it in equation form, but again, take that step beyond just, hey, here's a formula. Let's read the math. And the rest of this chapter, or maybe I should say the rest of the first half of this chapter, is really centered around this equation. It's centered around the idea, what is this saying? This is saying, will the momentum change or will it not change? Well, when will momentum change? Momentum will change if There is some applied force to it. And notice it's net force. So I would put it a different way. What if the net force is 0? What would you say about that? Momentum doesn't change. Sound like a conservational principle? And that's about where we're headed here. Conservation of momentum. Technically, linear momentum, because in the next chapter we're going to get a rotation, or what we'll call an angular momentum. And so this is that whole starting point. In fact, if I were to rewrite this equation using my calculus, I would say the change in momentum, or at least the differential of it, would be the net force multiplied by a small moment in time. If I were to integrate both sides of this equation, I would say from some initial momentum to some final, the left-hand side of this equation is then really the change in momentum, which these are all vectors, so let me make sure I put a little vector symbol over them. And so the change in momentum is equal to the net force added up over time. In other words, there's two things that determine the change in momentum of an object. One is how much force, and the other is how much time do you apply that force. You can imagine a really large force, but for a short moment in time isn't going to give something a whole lot of momentum. But on the other hand, maybe you could imagine then a small amount of force over a long period of time. Wouldn't that give it a lot of momentum? And so it's both of those together. And maybe a silly example is something comparing a baseball, as we soon get in here to opening season here, and say, okay, look, could a baseball, say, go flying at 80 miles an hour? Sure. And then how? I mean, one option is you hit it with the bat. And so there you have a huge force on the ball, but I would say for a small moment in time. There's contact with it, real large force, short amount of time. If I was making a graph of this force versus time, I would say no force on the ball, no force on the ball, crack, large force on the ball, and then it leaves the bat. No force, no force, no force. And this little equation is really saying this is the change in momentum, the area that is represented inside of that graph. That is the change in momentum. This ball went from, and let's just say I was just, kind of tossing the ball up and hitting it. I would say, okay, for getting the up and down, I would say, okay, it's really not moving. But then after I make contact, it is. And so I went from almost no momentum to a lot of momentum. And I did it over a short period of time. On the other hand, that same baseball, somebody could stand on a mound and take a wind-up. And although their force that they put on the ball is not that great, they can do it for a long period of time as they go from their hand in the back to the front, and meanwhile stepping and rotating their body. And that whole contact time, that would be far more of a contact time than the ball being hit with the baseball, could result in the same speed at 80 miles an hour as it comes off the pitcher's hand. And so I would probably describe that force on the baseball something like this: no force until we make the throw, then a small force, a small force, a small force, a small force for a long period of time. Couldn't that be the same area? So doesn't that give the baseball the same momentum? Exactly. So momentum is the total of both of those together. It is both the force and the contact time. You might see it in the same way if you happen to be trying to catch the baseball. You happen to go to, say, a Dodger game. You're in the outfield bleachers, and here comes this home run ball, and you want to take it home as a souvenir. You're going to catch it. How do you catch it? Hopefully so it doesn't hurt your hands. Just stick out your hand and grab it? Nope. Most people don't do that. How do you catch the ball? Maybe you've played that game, the egg toss game, where you take a friend Usually it's a bunch of friends, so it's a competitive nature, and you take either an egg or a water balloon, right? And you toss it to your friend, and they catch it. And if whoever catches it and doesn't break it takes a step back, and you toss it again, and then they catch it. And then this continues until pretty soon groups of people are really far away. And it's not just a toss, you're chucking the egg at them and saying, can you catch it without breaking it? Who lasts the longest? And of course, how do you succeed in catching the egg without breaking it, or the baseball without hurting your hand? What do you do? It's a contact time, right? You are both after the same goal, and that is to stop the object, and so the change in momentum has to be the same. And you can either have a large force in a short time, which would be here, or a small force over a long period of time. So instead, you put your hands out and you say, okay, and then as it comes in, you grab it, and you are slowing it down over a period of time. And hopefully with a small enough force that the egg or the balloon doesn't break or your hand doesn't hurt. Crumple zones, seatbelts, airbags, they all fit in that same category. How could we make an automobile safer? How could we make a train safer? Well, during a collision, the car is going to come to a stop. You have to change the momentum. Now, obviously, the faster the car is going, the larger the momentum is going to have to change by. So, to keep the occupants safe, it does become harder and harder the faster they are going. Okay, but for the sake of discussion, let's say the speed is 45 miles an hour, whether that be a train or a car. The idea now is to take the moving passenger and to go from 45 miles an hour to a stop without hurting them. So, what's the key? Well, the key is the long contact time. So if this is a seatbelt, the idea here is as the car comes in, put the seatbelt on the person, but then also, and I think we forget this about a seatbelt, but maybe you've seen the crash dummies, they stretch. And they're designed to stretch. Now, hopefully not so much that you hit the windshield or the dashboard, because then the stopping or the contact time is very, very small, which is your whole martial art thing, right? Can I use my fist to break a board? Well, you need a lot of force to that. Okay, how do you get a lot of force? Among other techniques, it is short time. Do it quickly. And the lower the time, the greater the force. And so, do you want a lot of force? Do you not want a lot of force? In the case of an accident, the answer is no, I don't want a lot of force. I want the occupants to move away. So whether it be an airbag that then is increasing the contact time, a seatbelt, which is then stretching, increasing the contact time or the stopping time, or whether it be crumple zones in the car. One of the manufacturers, is it Volvo, who has the drop-away engine under heavy impacts? I mean, it's got the whole front end is crumple zone. So the car hits, engine falls out, compresses on down, and you walk away. Ferraris, race cars are really known for that. The little parts break off. They, what you might call, take the energy or momentum away separately, so the driver walks away unscathed. Well, I'm probably spending too much time here. There's a lot of examples we could do with this, but this is that beginning step. What is this momentum? And this equation, I boxed around it. This is in the integral form. This is what I'd call the differential form. Both of these, you will see this, the first half of the chapter is all simply based around that. In fact, this right here is Monday's lab. Monday's lab, you will come in and you will run an experiment. It'll be one of these little carts here. And you will hook a rubber band to it. And you will give it a little push, and so it starts off with a given amount of momentum, and then the rubber band stretches and then pulls it back. And your goal will be to say, let's measure this side of the equation. What is the momentum before the rubber band starts pulling on it? What is the momentum after the rubber band pulls on it? So you will get the two momentums. Then, while the rubber band is pulling on it, our little computers will be measuring the force every moment in time. And so you'll have data. And then we'll integrate that. And then we'll see, does the left-hand side equal the right-hand side? And basically, you'll just do that 3 times. So it is a good first lab on momentum. It is straightforward, and it follows a test day, which you probably means you are tired and have done lots of physics. So it's not a very long lab either. So it's a good lab to do next Monday. Well, that being said, let me continue, because this by itself, I would say, isn't as useful as what we're about to see. I mean, this right here, a lot of this could be explained by just using Newton's second law. There's no point in going as far as inventing a new quantity called momentum if that's all we do with it. I will point out that this did come from Newton's second law. Fair enough? Here's where the idea of momentum can get really powerful. What if I look at more than one object? You see, this discussion right here was just focusing on, say, the baseball, or the egg, or the passenger in the car. Great questions, but they're just focusing on one object. What if I have 2 objects? 3, 4. I mean, let's just start with 2. Let me define it this way. What if I have a 2-particle system? So there's kind of a new word, system. Well, let's talk about that. But this 2-particle system is also going to have no external forces. Well, there's another word there. Let me kind of describe it this way. So here is, say, object 1. Let's say it is moving along this way. And just to make sure I distinguish it as object number 1, I'll put a little subscript 1. This is velocity number 1. And it's initial. All right? Let's say it comes along and it interacts with object number 2. Now, there's a lot of ways it can interact with object number 2. Object number 2 could be not moving and it would just collide with it. Object number 2 could be moving towards it, and that's the one I'll draw on here. Object number 2 initially, it's moving towards it. Object number 2 could even be moving away, although if it's moving away from it, it must be moving at a slower speed than number 1, otherwise number 1 will never catch it and there won't be an interaction with it. Okay, but there's a lot of ways, like I said, we can have some interaction. So just because I have put V1 and V2 as going towards each other, please remember, there could be one not moving, they could be going in the same direction. I'm not trying to distinguish between those. But here's what I mean by the 2-particle system. Let me put a little dotted line around it. Obviously, the 2 particles is, I think, pretty clear. You got 2 objects up there. But what I mean by system is let me look at them collectively. Let me look at them together as a group, a system, not separately. Okay? You see, if I looked at them separately, which we have been up to this point, but here's where things are going to get a little harder. Let's look at them together. See, separately, I would say something like this. I would say number 1 comes along and has an impact with number 2. So is there a force on number 1 in that view? Well, yeah, sure, right? And of course, what did we just say? If number 1 had a force on it, then what would you say about number 1? It's going to change its momentum, right? Not a surprise. In fact, I could set this up pretty easily just by moving these carts out here towards you and say, yeah, that's not a real hard one to do here. I could come along and maybe I'll set it up this way. I could say, all right, here is 1 moving towards 2. They interact. See, and if I focus on just number 1, doesn't number 1 change its momentum? I mean, isn't it going that way? And now it's going that way. I don't even think it's going the same speed as it was coming in, right? Maybe it's going slow and this one's going fast. And now it's going fast. The other way even. All right, so there obviously is a change in momentum of number 1. Now, of course, not a surprise. There's a change of number 1 because there was a force on it, and it came from number 2. And then likewise, if I looked at number 2 just by itself, I would say, well, number 2 changed its momentum too, right? It had a velocity coming in, and now it bounces off and has a velocity going out. Well, of course it had a change in momentum. Wasn't there a force on number 2? Yeah. And of course, where did it come from? Number 1, right? In fact, if I were to write down in equation form those words that I just used, I guess it would look like this, and maybe I'll, to give myself enough room, start over here. I would say the change in momentum of number 1 is equal then to the force from number 2 on number 1, right? Now, let me point out here. Doesn't this say the net force, all the forces added together? So, what I'm also then saying in this picture is no external forces. And what I mean by that is there's nothing else out here pushing on number 1. In other words, here's my system. My system is made out of 2 objects. Do those 2 objects interact? Absolutely. But does anything from outside of the system interact with those objects? No, not yet anyways. That's the second half of the chapter. Okay, so this first part here is a system, in this case 2, that interact with each other, but not the outside world. So the simplest case we could really do to have a system. 2 particles, no external force. And I would say object number 1 does change its momentum. If I looked at 1 by itself. Let me look at number 2 by itself. Number 2 by itself, oops, I should put a vector up there. Number 2 by itself, I would say it too changes its momentum, doesn't it? Number 2 by itself does have a force on it. The net force would be the sum of all the forces, which is only from object number 1. And so I would say then, let's look at the force, and in this case, it is from number 1 on number 2. All right. So again, I'm doing really nothing more than past chapters, although this is Newton's second law written in the form of momentum. But here's where it can become quite useful. Let's look at the momentum of number 1 and the momentum of number 2. So not the momentum separately of the 2 objects, but as a system. Again, big new word, system. A system of particles. Okay? And again, I only have 2. You can imagine I'm going to go to 3 and 4 and 5 and eventually an infinite number of particles before this semester, or before this chapter is over, right? But this then is the momentum of those 2 objects. Well, let's see if we know anything about that. Let me see if I can answer by taking the derivative of both sides. I guess I'd have the derivative of the momentum of 1 plus the derivative of the momentum of number 2 would then equal to the derivative of whatever's on the other side of that equation. Fair enough? Well, what did we just say? What is the change in momentum of number 1? Isn't that the force on number 1 coming from number 2? And what did we just say about the change in momentum of number 2? Isn't that the force from number 1 on number 2? And maybe now you see where I'm going. What would you say about these 2 forces? Newton's third law. Exactly. You got it. Newton's third law, right? Aren't these forces equal and opposite? So it comes out to be 0. Exactly. And what would you take the derivative of in order to get 0? A constant. And so what we see here is as these 2 interact, individually their momentums will change, but collectively, as a system, what would you say about those 2? Total does not change. Sound like last chapter with conservation of energy? So we have here, we have conservation of, and I guess I should say linear momentum, since we will soon have a rotation or angular momentum. And I say soon, but I guess that's actually after spring break, next chapter. Okay. And so, put another way, I could say that the initial momentum, and I would have to put total, is equal to final momentum, and I would put total. And I guess what I mean by total is the whole system. So I'm not trying to say, make sure you hear this clearly, I am not trying to say that the momentum of one object does not change. It does. But what I am saying is when it interacts with the next object, it may gain or lose momentum, and then that amount of momentum will go to the other object. That's the proof I wanted you to see. So just like you saw us run through a little proof on conservation of energy for these last 2 chapters, this is our little proof to say this is why we care about this word called momentum, that it's a product of mass times velocity. Because what it does tell me is when things interact, the momentum of the individual particles will change, but the total of the whole system will not. Okay? Now, maybe by an extension of this, I can go on to the next step. Because I have put on the board so far just 2 objects that interact. What do you think would happen if I put 3 in here? 4? 5, 6, N. And so, maybe real quickly, you will see that it doesn't matter how many particles I put in there. All that is going to do is have more interactions. And the more interactions will just mean that this object will gain, and that one will lose, and that one will gain, and that one will lose. But when it's all said and done, the total momentum will not change if we don't have an outside influence. And that's important to notice, because the second half of this chapter is what happens if you do have a collection of objects and there is an outside influence. What are we going to do? Okay? And how do we get the behavior of that? But, like I said, we'll start with just no outside. So, maybe I could put here N particles. No external forces. And so, putting a little dotted line, you could see that I might have object 1, object 2, object 3, object 4, object N. And so we'll add from 1 to N. And I would say there is a change in momentum of object number 1, and that must equal the net force on object number 1. And the net force on object number 1 is the force from 2 on 1, and 3 on 1, and 4 on 1, until I get to N on 1. And the change in momentum of number 2 would be the net force on number 2, which would be the force from number 1 on 2, from number 3 on 2, from number 4 on 2, until I get to N on number 2. And then dot, 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 until I get to the change in momentum of the nth particle, which would be the net force on the nth particle, which would then be the force from the first one on the nth, and the second one on the nth, and the third one on the nth, and until I get to the nth minus 1 on the nth. Right? And of course, if I were then to add all these together, here's the same magical step. It was easier to do when we only had two objects, but you can see it comes out to be the same. Over here on this side of the equation, I would say when I add these all together, this is the change in the momentum of everything added together, total. What does it equal? And it comes out to be 0. You see why? Do you see that force from 2 on 1 is equal and opposite to that one? The force from number 3 on number 1 is not really listed here. It'd be this third one right there. Right? Equal and opposite. This force here and that force there would be equal and opposite. And so using Newton's third law, you're going to end up adding 0 to 0 to 0 to 0 to 0 and end up with 0. And so adding a bunch of zeros together, no matter how you do it, you get 0. So there's the change in momentum. And so simply put then, I could say that the total momentum initial is equal to total momentum final. That's the key recipe. Whether I have two objects or n objects, or as we soon will see, an infinite number of objects, none of that matters. The key step was no external forces. And so if I have no external forces, I have this conservation of momentum. Well, since it's a long chapter, I think now is a good time to maybe break from more lecturing. And let's look at some examples. As you notice, the first 8 chapters, I gave you all the material and then did examples and worked them out. But I think because this chapter is longer, and because I think that this first part's a little bit easier than some of the harder stuff, and maybe it's best if we focus on the easy stuff today as opposed to the harder stuff, which, given that your test isn't on this, you may not be quite as ready to digest the harder stuff yet. On Wednesday, you probably will be, assuming you've recovered from all your studyings from the weekend. But let's do some examples here. So let me kind of clean off the board here and say, let's look at some examples. And I'll say probably the easier examples might be the ones involving just two objects moving in a straight line. So I'll start there. And so let me take two objects that are moving in a straight line. That's why I brought the card out here, to sort of get us started. And I'll even start with maybe the easy one of saying, let's take this second cart and just have it at rest for a moment. And so scenario number 1 is simply this, that I will make cart number 2 moving with some speed. Let's just call it V. It has some mass. Let's call it M. Let's call it M1 to be specific. Now, in my case, the M1 and the M2 are the same amount. But maybe we should have a more broad discussion that what if they are different, which I can make them different in just a second by putting weight on one and not the other. All right, so it comes along, moving at some speed V, hits, collides, sticks together, and moves forward. What's the speed after the collide? Yeah, and it's half. I mean, let's run through it. You may not be able to do it in your head, and I wouldn't expect, and some of these are really hard, so I definitely would not expect you to do them in your head, but let's write it out. Here's the example I want you to see. What I would say is the initial momentum is equal to the final momentum. Now, granted, they are vectors, and so at this point, I'm really saying the initial momentum in the x direction is equal to the initial momentum in the x direction is equal to the final momentum in the x direction. It's just a simple one-dimensional problem. And one of them is even at rest. So when I start over here and I say, well, how much momentum do I have from the first one? I guess I would say it is m1 times v1 initial plus. Plus what? 0. Why 0? Because the second one's not moving, right? And so notice here when I say, what's the momentum? I mean the momentum of the whole system. It's not just one object. It's all the objects. But of course, in this first case, the second object is at rest. Okay. So there is the initial momentum. What happens to it? Well, I would say, given the fact that they stick together, I will view that now as one object. So, but that one object has a total mass. That's the two added together. And it would then be maybe final speed. And so solving this first and the easiest of the equations we could have, or the problems we could have, two objects, one stationary moving in a straight line. I could say then that m1 over m1 plus m2 is equal then to, or times the initial speed of number 1 is the final speed. And notice I didn't bother to put final speed number 1 or number 2 since they're hooked together. Okay? And in my case here, I would actually then say a little bit further, and so let me call this scenario A, where m1 is equal to m2. I would actually then get 1/2 of the initial speed of number 1 is the final speed. Fair enough? And that's what some of you already pointed out pretty clearly. You were thinking that these equations are linear. If you doubled the mass, you must have half the speed in order to get the same momentum. Exactly, right? And that's what I get after I did it. I can switch it up and do different things. Let me still leave the second one at rest, but now I will double the mass of the first one. And these carts and mass bars have the same value, which when you use them in lab on Monday, you'll see it's in the neighborhood of 1/2 kilogram. And that's, you'll have to measure. I think they come out to be like 508 grams or something like that. And so you'll weigh them. But for now, let me just call them the same mass. Let me call them 1/2 kilogram and just say, okay, now they come along and they hit. What's the speed after the collision? 3/4. Okay, good. Doesn't look like my... Well, and that's important because remember, no external forces, so no gravity here. All right. So I heard different answers, one of them being right, but let's work it through. I would call this scenario number 2. And I'd really go through the same thing, right? I would say initial momentum is equal to final momentum. And in this case, I would start exactly the same way. The first one's moving, the second one is not. They hook together, so I have a total. And so this would be the equation again. So this equation would be valid for this scenario also. Let me use that as an opportunity to point out this equation is not valid for every case. This is, or at least every case where we don't have an external force. Conservation of momentum. Now that being said here, let's put in what I have here. It looks like to me that number 1 has been doubled, and so number 1 is twice that of number 2 now. So I left number 2 alone, but I've doubled number 1. And then punching that in here, I can see that I would have a 2 plus a 1, that's 3 down here, right? Yeah, and a 2 up there. So this would be 2m2 up there, and a 3m2 downstairs, times the initial speed of number 1 is then equal to the final speed. Or, as some of you said, 2/3. Exactly. Well, I'll do one more, but you can see there's a lot of combinations we can do with this. And one more with that rest before we move to something else. I'll say, okay, what if I had that? What if I had the heavier one, twice as massive as number 1 here, and let it move and collide? What's the speed after the collision? Yeah, and now I hear everybody say 1/3. Right, totally agree. Each step here would be exactly the same, which would end up with this formula to be exactly the same. The difference being, of course, I have now made M2 twice that of M1. And so as I substitute this in here, I guess I would have something like, and I'll do an M1 on the top, and in place of M2, I could put a 2M1 and get 3M1 down at the bottom. And so I would come up with 1/3 of the initial speed is equal to the final speed. So again, see how this principle is allowing me to find out questions like what is the speed after the collision? So we have an interaction. And did you notice the best part of this? How much force did they put on each other? Don't really know. How much time did it take for the collision to happen? Don't really know, do I? And so this technique completely avoids that set of issues. It's kind of like we did in the last chapter. We dropped something and we said, how fast is it going? Down at the bottom. Did we need to worry about what was the force of gravity? Or how much time did it take to get there? That was the neat thing about it. We were able to get out the same answers looking at it from a different point of view, and those little details we didn't need to know. And I would say the same thing here. I don't need to know how long the collision took as one collided into the other. I don't need to know how much force was actually there. I don't know if it was, and my graph has since been erased, whether it was a large force for a short period of time or a little force for a short period of time. Now, if I wanted to know more details about the force, then I need to do it some other mechanism than looking at momentum. But if my goal is to find what is the speed after the collision, or if I know the speed after the collision and I want to know the speeds before the collision, then I don't really need to worry about the details of the collision. And that's why it becomes a powerful tool. And that's why we introduce it to you as yet another tool in your toolbox to figure out what is or is not going to happen, or what was not happening before the collision. Say this is an automobile investigation, and you see the aftermath. And you've got to put together the pieces to figure out, well, what happened before the accident? What was going on? And we know that there's this principle called conservation of momentum, and we can put that all together. But let's not stop our discussion here. Let's continue with these examples. Let's take, say, scenario A, even B, and scenario C. Let's keep talking about them. Let me keep talking about A first here. And I think what I've got so far is that one was stationary and one was moving with some initial speed. Then they hooked together, so they were both moving with a final speed, and that final speed was half the initial speed of the first one, right? What about the energy? I mean, let's take this back one chapter. Wouldn't you say the energy is also conserved? But be careful with that word conserved. Does that mean that the kinetic energy before the collision is the same as the kinetic energy after the collision? I mean, let's just write a couple of equations on the board. Let me do this. What about the kinetic energy initial? I guess I would write that as 1/2 times m1 times v1 initial squared, right? That's what I would say is the kinetic energy before. If you wanted me to make it more complete, I would say plus 0. Well, why the second one and why 0? Well, the second one was stationary, wasn't it? Okay, let me take off the mass bars. Here it is. Here's the scenario before the collision. That one's moving, that one's not. That one has kinetic energy, that one does not. That would be the total kinetic energy before the collision. Also, I'll call it Ki. But what about Kf? What's the kinetic energy after the collision? Well, they collide, they stick together, right? They're moving with some final speed. Thinking of that as one object, I would write this as 1/2 m1 plus m2 times final speed squared. Fair enough? Are those two necessarily equal? Many of you are shaking your head no. Why would you say that? I thought we had conservation of energy. We do? We do?
Isn't some loss in the friction?
Right. And so be careful here, right? It's not conservation of kinetic energy. It's conservation of energy. So we could have something like this, as fair enough. If we look at all the energies before and compare it to all the energies after. Let's talk about all the energies before. Now, I think in this problem, there's no point in putting a spring in here. There is no springs. I don't think there's any point in putting a, what other ones did we have in there? A gravity. It's a level ground. Good. I guess I would just say that the energy I have to begin with is all kinetic. But you see, it's the other side of the equation that says it has to equal to the final kinetic, and it could have some heat. Right? Now, wait a minute. Doesn't the heat come from rubbing and friction? So, I thought the point of this discussion was to take an object with no outside influence. I mean, is there any friction here? Okay, not much, negligible, right? So I ask again, so is this number 0? It's not. And why not?
Objects collide.
There's rubbing here. All right, so I want to make this clear here, right? That conservation of energy does not necessarily say these two have to be equal. We can have some heat that is formed in the collision. And to make it clear what heat I'm talking about, I am not talking about a heat created because of the friction between the ground, or in this case, the track and the cars. That I've already said is 0 or negligible. I know I said that because when I started this problem, I said that the initial momentum is equal to the final momentum. What was the condition for that to be true? No outside forces. So as I draw a circle around those two carts, I would have to say I am assuming in this problem that there is no friction between the cart and the track. That is what I did right here. And that's my little warning to you, like we've pretty much done in every chapter. You have to realize, where do these principles come from? What is their foundational framework? You can't just pull them out of the air and try to apply them. They may not work for that scenario. They have their limitations. You need to see where they are derived from. You need to know when you can and cannot use them. In the last chapter, we made a real big deal out of it when we said things like using 1/2 kx squared. And if you're going to use that equation, sure, but it has an important restriction. And as you're getting ready for the test, let me just remind you, that important restriction is you must call x equals to 0 the natural length of that spring, right? That's what it was derived from, Hooke's law. And so my freedom of choice is to choose to use that equation. But once chosen, it has power over me, and I must use x equals to 0 at the natural length of that spring. And I'm saying the same thing here. If I choose to use momentum to solve this problem, and I call it a conservation of momentum problem, I know that the conservation of momentum is only valid if I have no external forces on my system. And so whether I admit it to myself or not, but I need to realize it as I move forward in the problem, that I am admitting to myself that there is no friction between here. So to say that I get some heat because of the friction between the track and the cart means I have just violated the assumption I made when I started the problem. That does not work well. You will get things wrong that way. You will build prototypes that will crash and die. Well, hopefully no one will die in your experiments. But they will be expensive, very expensive. And the product will be late to market. And you may lose that edge. And it'll cost maybe millions of dollars for that company. Okay? And like I said, all these things are what makes the difference between the good scientist and engineer, the thriving scientist and engineer, and the okay scientist and engineer. The one you don't want leading the team, but you need to keep around for other reasons. I don't know what. Okay? And so that is an important piece. But as many of you already pointed out, there is some other rubbing going on here. And that rubbing is very clear. That rubbing is this cart rubbing with that cart. And so as they pound together, I was probably a little too hard there, but as they pound together, these molecules here push on those molecules there. The result of that is these molecules are probably now moving much faster than they were before the collision, and hence there is the possibility here that heat is created. And in fact, it is hopefully so obvious by now. Let's put in some numbers here. Using what we did in scenario A, I would say these two added together come out to be twice mass number 1. And final speed number 2, as we already derived earlier, using the principle of conservation of momentum and tying it together with the principle of conservation of energy, would say that I have then 1/2 times the initial speed squared. And now running through some arithmetic here, that 2 cancels with that 2, that 1/2 is squared, and I end up with 1/4 m1 v1 initial squared. And so does that number equal that number? All right, it does not, does it? And so there's my mathematical proof to say, I think there was quite a bit of interaction going on between cart 1 and cart 2 that made the molecules go faster. There is some heat here created. I guess I would say this much for sure, though, because of conservation of energy. That number won't be bigger than that number, right? I mean, look down here, right? Can that number be bigger than that number? No. But it is quite possible that that number be smaller than that number. And in fact, that's what we see here. In fact, if I continue on with this problem, I could say, well, how much heat is created? And I guess it would be the initial, how much energy really did you start with, minus what still remains as kinetic energy. Which, as you can see, if you take a 1/2 and you subtract a 1/4, you're going to end up with 1/4 m1 v1 initial squared. And so I would say here that I have a scenario where the amount of heat that is formed in the collision, and I'll say it again, is not coming because of the rubbing or the friction of the carts with the track. It is the rubbing between the 2 carts. And that heat that is created is as much as the kinetic energy that is left over. And so half of the energy went to heat, and half of it still remains as kinetic energy. Of course, let's look at our other examples here. Scenario B, we had a different relationship in our masses. And so if we continue our conversation about energy for scenario B, let's see what happens there. Now that we just spent a long discussion on them, I think you can see that scenario, which was scenario B? Oh, we had the mass bar here. So in scenario B, this mass bar here, there it is, an interaction. Now I'm thinking there's some heat here too. Now, maybe not half, I don't know yet. But let's run through the mathematics. And I guess I would do something like this. I would say, okay, what is the initial kinetic energy? And it would be a 1/2 m1 v1 initial squared. What is kinetic energy after number 2? Well, this one, I guess I do see that I have the objects now hooked together. So together it's 3m1, but it's traveling with this speed of 2/3. And so I would write it as 1/2, and it would be a 3m1. It's probably the best way to describe it. And then the final speed is the 2/3 times the initial speed, and I'll square that. Now again, running through a little bit of mathematics, maybe I'll just do a couple steps so you can see it. There's the 3/2. This right here would be the 4/9, and then I'd have the m1 v1 initial squared. It looks like this 2 would go into there. It looks like this 3 would go into there, and so I would have 2/3. Did I mess up my math here? What did I do here? Isn't that bigger than that one? I have 1/2. How much mass do I have? 3. Oh, there's my mistake. It's not 3m1, it's 3m2. Right? Yeah, so m1 is, okay, much better. All right, so it's 3m2. All right, so m2. Let me take one more step, because m2, back to m1, if you will, right, is half of m1. So this would be 2/3, and then m2 is half of m1 v1 initial squared. There we go. Then I can cancel that, and I end up with a 1/3 m1 v1 initial squared. And of course, what I wanted you to see is that this number is not the same that I started with. So clearly there was some interaction, clearly there was some heat. Again, notice where the heat is. The heat is in the interaction here between two carts. It is not between the rubbing of the track and the cart. And if I were to ask then this question about the heat, how much heat then is formed, I would say there is the kinetic energy you start with, and then you, of course, minus what you are left with. So this is a 1/2 minus a 1/3 at 1 v1 initial squared, which as a common denominator of 6 would give me a 3 minus a 2, which is a 1. And so in this case, there is some heat that's created, but not nearly as much as heat that was created in scenario A. Scenario B, yes, still has heat, but not as much. And maybe I should have even put, scenario B versus scenario A. And this third one here, scenario C. Scenario C, I would say, here's the initial kinetic energy. It's 1/2 m1 v1 initial squared. And then the final is 1/2, and what do we do on this one? We put the mass bar on this side. And so when they hooked together, they were 3m1. That's true. That's the smaller one. That's 3. Okay. And then the final speed, as we worked out before, was 1/3. And so it's 1/3 v1 initial squared, whole thing. And I guess I would argue that one of the 3's here cancels with one of the 3's there. So I still have another 3 with another 2. So that's a 1/6 m1 v1 initial squared. And sure enough, that number is smaller than that one. In fact, that one's a lot smaller than that one. So I'd say this one is quite a bit of heat is formed. And if I were to write it out and say, okay, how much heat is formed, I would take the 1/2 m1 v1 initial squared and subtract the 1/6 m1 v1 initial squared. Obviously, I get a common denominator of 6. This is a 3 minus a 1, so that's a 2/6, which reduces to a 1/3. So, is it really? 3 minus 1, 2. Yeah, okay. 1/3 m1 v1 initial squared. So, there is my... That doesn't seem right. Shouldn't be a third plus a sixth. Should get a half. Oh, and it does. Okay. All right. So, so you see it, and I hopefully you then saw really the strategy here at the beginning part, and that is simply when we have two objects interacting, or perhaps 3 or 4 or 5. There's no outside influences. Then we can say we have conservation of momentum, and because of that we could probably go through a couple steps and get their speeds, and given their speeds we can say something more about their energy. And so we can put together the chapter that's on energy, which you are studying now, together with the chapter that you will be doing over this spring break, and say let's look at the energies involved, let's look at the momentums involved, and see if we can come up with the answer. How fast is it going, or how much heat is created, or whatever the question may be. Mine was kind of a linear process of find the speeds, from the speed find the kinetic energy, and from the kinetic energy find the heat. But it's not always working that way. Sometimes they make the problem a little less direct. And they say you have a collision, you have a certain amount of heat that is created. From that, could you tell me how fast it's going? Or from that, could you tell me the mass that the object had at the beginning? Or could you tell me the speed that the object had at the beginning, or objects have at the beginning? And so basically it's going to take you putting together both principles, conservation of momentum together with conservation of energy. All three of these cases would fit in the category called inelastic. And so when you hear the word inelastic, basically what happens in an inelastic collision is there is a change in the kinetic energy. Simply put, a description called inelastic is meaning that the energy that started as kinetic then went somewhere else. Now the reason I say somewhere else and not just heat, because the three scenarios I just gave you were obviously heat. But if this had been, say, again, an automobile accident, that energy could be energy of what we call deformation. You actually have a bumper that has now been bent, and that's going to take a certain amount of energy to bend it, and it will take a certain amount of energy to unbend it. But you got to bend it, you got to move the molecules around there, and that takes energy here. And so your author has a little section that he talks about the energy of deformation. Mine did not deform, so I just said it must. If it's not in kinetic energy, it must be in heat energy. That's probably the best way to describe where did the energy go. And this is, like I said, all of these are inelastic. Actually, all the ones I've done so far are what your author will even call perfectly inelastic, which is really code word to say they stuck together. And so you might hear that once in a while, perfectly inelastic. And of course, perfectly ineelastics are usually the easiest ones to do. It's why I did them first. Why are they easy to do? Well, what do you know about final speed? Yeah, you know that the final speed is the same, right? Because they stuck together. In fact, maybe I should put that back here on the board here. If you do come across this word, perfectly inelastic, and you probably will. Final speed of number 1 and final speed of number 2 are the same. They are connected together. And like I said, they usually end up being the easiest ones to do. and mostly because you have the fewest number of variables. And again, you see that right here. It was pretty easy then to say I can just think of this as one object. Now I'm moving with the same speed. But let's change that. Let's change it from being perfectly inelastic. Let's not have them stick together. In fact, let's do this one here. Let's do the one where they not only do not stick together, but they don't even get a chance to touch each other. Kind of seems like I still have, well, maybe that's level. Maybe not. But I think close enough. But here's one where this comes in, and if you can look real closely, the magnets, the magnets interact before they can touch. Now, if I did it really hard, I could get them to actually touch. But if I do it just slow enough, they will put a force on each other via these magnets that are buried inside. So the molecules here don't actually touch there. So let's talk about that one. I mean, obviously it's not perfectly inelastic because they did not hook together. But they're even something better than that. Because, and maybe you see it coming here. How much heat do you think is going to be created here? I'm thinking none. Why would you think none? Yeah, they don't get a chance to rub. Exactly. Now, if they don't get a chance to rub and then don't get a chance to create any heat, then what would you say about the kinetic energy before and after? Yeah, I would say then the kinetic energy before and after are equal. Yeah. Let's see if that's the way it comes out. In fact, maybe I'll just put that word on the board here. Elastic. These, maybe I should put them together here. Are elastic collisions, then the initial kinetic energy is equal to the final. Or maybe said the same way, no heat is formed in them. And so kind of just giving words to describe all of this, we will always be using conservation of momentum and conservation of energy. So let's look at this elastic collision. Or maybe I should say, let's see if it even is an elastic collision. But I would start off the same way as I did before. Initial momentum is equal to final momentum. And of course, when I do that right away, I am implying that these two objects will interact. There's forces between them. They individually can change their momentum, but only because of the interaction between these two, not because of the interaction with the track. So there's a 0 to negligible amount of friction. You have lost your privilege of being cart number 2. All right, so we have that. Okay, and so this description here is still valid. And maybe I should emphasize that conservation of momentum has nothing to do with these words. Did you catch that? Right? Conservation of momentum is true based upon, do we have an outside force on there? End of story. So do we have conservation of momentum in elastic collisions? Yes. Do we have them in inelastic collisions? Yes. Do we have them in perfectly inelastic collisions? Yeah. These words don't describe whether or not we have conservation of momentum. The conservation of momentum was determined whether we had from outside influences or not. Those words are describing something that happens with the collision itself, whether heat is created or not. If no heat is created, then we call it elastic. If some heat is created, then we call it inelastic. If the heat that's created is in such a way that the two objects are stuck together, then we call it perfectly inelastic. Which, by the way, without proof, this is implying then if two objects ever stick together, it is inelastic, and the kinetic energy then will be less than what it was before. And I'll throw that out there. I won't necessarily prove it right now, but your author goes through that, and he says the reason we call this perfectly inelastic is you can show that if two objects stick together, then you got to have some heat. You can't have conservation of momentum, have them stick together, and then the kinetic energies be the same. Those equations do not match up. They don't work out. So if they stick together, you got to have some heat created. But again, let's just look at this scenario and see is any heat created. And again, the second one is stationary. So I would say this is an M1 V1 initial plus 0 again. And maybe we should watch it real carefully because there is a clue I want you to see. The second one is stationary, first one is moving, but after the collision, what do you notice? The first one is now stationary. All right, so what I'm going to put is 0 plus M2 V2 final. And so what is the final speed of number 2? Well, it looks like I changed orders. Speed number 2 final. Keep it consistent with what I started there. I guess that would be the ratio of M1 over M2 V1 initial. And so I definitely get a different equation than I did when they were stuck together, don't I? And in fact, this is a good example where, again, to answer these questions, you've got to go back to the fundamental physics of conservation of momentum. There's not some big long set of formulas that you'll want to remember in terms of, hey, what is the speed after the collision? Everyone is unique. Everyone is different. You've got to ask what's going on. You've got to go back to the fundamental principles. And that's what we keep emphasizing here. What's the fundamental principles of nature? I'll say it again. There it is on the top of the syllabus. It was on the top of your first test. It will be on the top of your second test come Monday. Physics is about knowing how to apply a few powerful fundamental concepts to explain a universal phenomenon. And so we will have lots of things that we can explain. And we can get them all from really some very simple basic principles. Newton's laws of motion, conservation of energy, and conservation of momentum. Those are the three big things we've learned so far. That's it. 10 weeks into the class. How hard can it be? You've learned 3 things. Right? All right. So there is that equation. Now, in my case, which I'll call it scenario A, what did we notice here is, of course, that the first one stopped, but also I noticed that the masses were identical. So what would I say then about the final speed of number 2? It's the same as the speed of number 1. And of course, now thinking about it conceptually, that probably doesn't surprise you. You're like, okay, that one essentially lost all of its momentum. In order to conserve momentum, that has to take all of it. Since it has the same mass, it must have the same speed. And so there's your deductive reasoning to come up with that. It must have the same speed. Here is that same deductive reasoning mathematically. You come up with the same speed. If I would start to ask the question about the energy, I would say, well, what is the initial kinetic energy? Well, just like before, it would be just the first object moving because the second one is stationary. And what is the kinetic energy after the collision? Well, it'll be 1/2 M2 V2 final squared. But as we just pointed out, for this case, M1 and M2 are the same. So let me replace M2 with M1. And as we just pointed out from conservation of momentum, that speed number 2 after the collision is the same as speed number 1 before the collision. So I could write this as V1 initial squared. And of course, how does that compare to that one? They are the same. So what does that tell me then about the heat that's created here? 0. No heat is created. There was no loss in the kinetic energy. This does fit this idea that I was saying. This is an example of elastic collision. So some collisions we may actually have an interaction. We actually may have molecules rubbing and bumping between object 1 and object 2, and we will get some heat that's created. But other collisions will be done a little bit differently, that the molecules will not rub and bump and create heat. I should even go further. Just because they actually touch doesn't necessarily mean heat is created. Because what could happen, as often happens in what we might call the crash bumper or the spring bumper, is that you could come together and the bumper then compresses with a spring and then ricochets off. Bing! And so essentially during that collision, there was a momentarily decrease in kinetic energy. But not that it went to heat, but it went into the compressing of the spring. And then as it bounces off, that energy that was stored in the spring gets re-established as kinetic energy. And so you don't have any loss in the kinetic energy. But yet you do have a contact that was made. There probably always is a little bit of always bumping and rubbing going on. So to say something is elastic is really kind of saying it is just barely inelastic. And so things that, don't deform and don't create any heat is not quite true. Oh, but I think you see the idea here. How about if I switch it up a little bit? How about scenario B? Where now I have a collision where the first one is twice the mass of the second one. Now, still starting at rest, but I think we've got a little harder problem here because there's not much I know about the ending here. Watch carefully. What do you notice? First one's still moving, isn't it? It didn't stop. So I'll call this scenario B, but I do really need to come back here because I can't just use this equation down here, right? Now I do need to come back up here and say what's different in this case? And isn't it right here? And so let me erase everything from here forward. And say, what's going on now? Well, I guess now I have object number 1 now has a final speed. And object number 2 has a final speed. And if I then even put in what is given for scenario B, there's not a whole much more I can do with this. If I just say that number 1 is twice number 2. I mean, I can put that much in here. I can place of number 1, I can put twice number 2, V1 initial. Yeah, I can do that much. Here I'll leave number 1 and have final speed of number 1. In place of number, no. That's not quite what I wanted to do, did it? So in place of number 1, I will put twice number 2. And in place of number 1, I will put twice number 2. And then number 2 I will leave alone. And then I've got something I can work with. I can cancel that off. But really all I get here is a relationship that simply says that twice V1 equals to twice V1 final plus V2 final. And at least that by itself, I'm not sure I'm getting anywhere. Albeit true, that's, unless I am told more, doesn't help me much. Of course, last time it helped me because I did notice that this one had stopped, so I could actually come up with something. This one, I do notice the following, that speed is pretty small. Which of course is, and I say small compared to that one, which is why this number is bigger than this first term. That's why this has something. And it was a pretty big one, right? I mean, you saw that here, right? This one's moving along. Yeah, that one went way down. But that one's pretty big. And so that would be the mathematical relationship between those two. And so it's kind of difficult to even do the next step, which is how much heat is formed without knowing more. In fact, I couldn't do anything. However, we may come at from a non-linear approach, and that's what I wanted you to see. What if I were to tell you, as by observation, that these things interacted with magnets, they never really touched on each other, and hence it is an elastic collision. So instead of me trying to prove is this elastic or not, let me change the question to say I'm going to give it to you that it is elastic. What would that do for you? So maybe I would say given that it's elastic. What would you say there? Yeah. Kinetic energy is conserved, right? And I would say, okay, 1/2 m1 v1 initial squared is then equal to 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. And then if I did my substitutions for this given case, and I'll just actually do one step of mathematics, get rid of the factors of 1/2, just to make things a little easier to see and to write. But I would write this then as a 2 times m2 v1 initial squared is then equal to 2 m2 v1 final squared plus m2 v2 final squared. And then, like we did with the momentum, but now we're dealing it with energy, and again, let me point out, that's I think one of the challenging things about this chapter is we got the new material called momentum, but we got to also tie it in with all the other stuff we've learned before. But it looks like I have something that is a bit more complicated than before. It's got a 2 m1 initial squared is equal to a 2 m1 final squared plus v2 final squared. And so now if I wanted to find, say, the final speed of, then I can't decide if I want to do final speed of number 1 or final speed here of number 2. But I now have that ability, because don't I have 2 equations and 2 unknowns? And to save a little time here in class, let me not go through and work this out. Because again, it's not so much I want you to see all the mathematics that needs to be done here. What I want you to see is we need to go back to the basic principles, write out what's going on for this scenario, and then solve the math for that scenario. And what I've done so far is that I have put this momentum here, if you will, in terms of the second one not moving. You could see that the equations would even get more complex if that one was moving. And I think our time will be better served if we go ahead and let's just go right to the grand finale. Well, let me not bother to solve this one. I could, right? I could solve this for, say, V final 2 and put it into there, and then I'd have a long equation for V final 1, and I could solve it for V final 1. And once I have V final 1, I can come back over here and get V final 2, right? But as long as we're going through that much algebra, why don't we just write out really the general case? The general case might look something more along these lines. I might have two objects that have different masses, so M1 and M2. They both could be moving. So this would have some initial velocity and this would have some initial velocity. They then might hit each other. So maybe this has a small speed, this has a large speed. And how do they hit? Do they hit to the point where the materials actually touch and heat is created, or do they not and no heat is created? See, if you put all those together, I guess I would say, here's what I have. I have conservation of momentum together with conservation of energy. And in the conservation of momentum, I would write it this way. I would write it as M1 V1 initial plus M2 V2 initial. That then equals M1 V1 final and M2 V2 final. That, I would say, is the final point I'm getting at. I started with the easy ones. But as the second object is now moving before the collision, and both objects are moving after the collision, this is what I would have. And what do you think I would have if I had three objects? Another term on each side. And 4, and 5, and 6, right? And so, again, what will serve you best is not that I solve some equation for some special case. Well, but you realize that this is a fundamental principle that can be used to solve a lot of different problems. And so you want to start always at that fundamental principle, which in this case is momentum. Whether or not some of these are zeros all depends on that particular case. And so I will write out what I will call equation number 1. It's the principle of conservation of momentum. It's the point I'm getting at in today's lecture. I have conservation of momentum. And maybe I should realize and emphasize again that I have conservation of momentum if there's no outside forces, because we still got to talk about the other half of this chapter about what if there is outside forces. Okay? But this is without outside forces. Let's put the energy up here. I would have something that looks like this. I would have 1/2 M1 V1 initial squared plus 1/2 M2 V2 initial squared. That would be the kinetic energy before the collision, both of them moving. And then after the collision, again with both of them moving, would be 1/2 M2 M1 final squared plus 1/2 M2 V2 final squared plus, and I'm going to go ahead and use the symbol Q for heat now. I kind of mentioned it one time before, and up till now I've just been kind of spelling out the word heat, but I'm just going to put a Q there. So I'll put the Q for heat. I'll put a box around that because I would say this is scenario number 2. Or maybe I should say equation number 2 for that same scenario. So you can see I have two equations, which means I can solve for two unknowns. So if I was going to actually solve this equation, they would need to tell me enough information except for 2, right? They tell me any less than that, I don't have enough information to solve it. Agreed? I mean, basically what I have here is, and this would be a typical type of question. A typical type of question will tell you what is the initial speed of each object. What is the mass of each object? And then maybe it would tell you one more thing, like it's elastic. Because what would that tell you? No heat. So Q would be 0. And then the only two unknowns are the final speed of number 1 and number 2. And so if that's the case, elastic collision, then we could work out an equation for what is final speed 1 and final speed 2. And your author does. He takes about a page and a half. He goes through it. And if we got time, we'll go through it. But I don't think going through the math is the important part. The important part is knowing that these are the two equations you would do. And even those are kind of limited. Aren't we only having a one-dimensional collision? Yeah, so let's expand this a little bit too. Question.
I was just going to ask, can you use that one for an elastic collision? The first equation?
Yes, let me say it again. I'm going to come over here. Look at these words, elastic and inelastic. They have nothing to do with conservation of momentum. A collision is elastic if no heat is created. A collision is inelastic if heat is created. Both cases, momentum is conserved. And so I think you saw in my two little examples I was doing, or yeah, one where they stuck and the other ones where the magnets interact. I had elastic, I had inelastic, but all of those I used the principle of conservation of momentum. Okay. And so this, again, I would call is almost to the grand finale. Not quite. Grand finale gets me to the point of what if this is a two-dimensional collision? And I won't even go to the grand finale. Let's just do a two-dimensional collision with one of the objects stationary. Yeah, too bad this ended up on the middle board. I'll leave it there on the middle board here. But what if I had something that looked like the following picture? Because I don't think your author goes any further than two-dimensional collisions with one being stationary. Let me double check that, but I put that in my notes that that's as far as we're going to get for us, which is pretty far. I mean, that alone is hard enough here. So if I had something that looked like this, I had, say, object number, 1, moving with some initial speed and colliding into object number 2 that's stationary. Then what's going to happen is object number 1 is going to ricochet off and have some final speed. It's going to force then object number 2 downward in some direction. That angle that it reflects or scatters maybe is a better word. And I want to use the same symbol, theta and phi. So he uses theta and phi for the angles. And he uses theta for the angle that number 1 ricochets from, and phi for the angle that number 2 then deviates down. But again, if this is a collision with no outside influences, so maybe an example would be two hockey pucks on ice, which I know, winter sports are such a big thing here in Santa Barbara. But pick that because of the ice, the ice being low friction. And that was the condition of conservation of momentum, that we have no outside influence there. Sometimes we'll use examples, the game of billiards, pool. That's a little more complicated because you have things rotating. We haven't talked about things rotating yet? That's chapter 10 is, by the way. And so I'm not sure those are the best of examples quite yet, but air hockey might be another good one. I guess both air hockey and regular hockey, you usually don't have two pucks out there though, but anyways. Yeah, but something where, shuffleboard. Is that the game that, again, for all of you who live in senior citizens' homes, you're used to the shuffleboard game. But anyways, both of those probably not good examples, but curling, yeah, there's another good winter sport for Santa Barbarans. Yeah. But all of these ones where we have two things colliding, not rolling, on a frictionless surface. This is what we're talking about here at the beginning. And so, as I write this down, I would say that I have a conservation of momentum. But here's where I gain an additional equation, which is probably really good because I have gained an additional amount of complexity to my problem. But I would have then these three equations. And that's what I wanted to compare and contrast. So this one-dimensional one we've been talking about for the whole time has really been right here, where I have the momentum is conserved, but it was really only the x direction. But we started this whole discussion by saying momentum is a vector, and so we have to look at the x component and the y component. And so a harder problem would be a two-dimensional ricochet of atom 1 hitting atom 2. And maybe that's a good one, two atoms colliding. Again, we can't see them with our eyes. But as they ricochet off here. And so we would apply, and then this is what I want you to see. We would do conservation of momentum, but we would now have two equations to go with those two dimensions that are going on. Now in this case, I made it a little bit easier on myself because the starting scenario is only one-dimensional. So as I were to put in my equations, I would say the m1 v1 initial plus 0 would be the way to calculate the initial momentum in the x direction before the collision. And in the y direction, it would be even easier. It would be 0 plus 0. The first one is not moving at all in the y direction, and the second one still is not moving. So that would be my initial conditions. Whereas after the collision, I would have object number 1, so it would be m1 v1 final, but then I would have cosine theta because I would want to know how much of the momentum is in the x direction. It is not just moving along in the x direction. And then likewise, the second object, which has a momentum of m2 v2 final, would then be multiplied by sine of phi, and I guess I should even put in the negative there for saying that that would be a downward direction to the movement. At least, I'm getting ahead of myself. I already moved to y. Sorry. Plus cosine phi. Keep looking at the time. I want to make sure we finish this part of this half of it so we can really dive into the harder half next Wednesday. And have time to do examples before you go off for spring break. But this would be then the equation for the x direction. And let me emphasize it again. I would not in any way encourage you to memorize this equation. That's not the point at all. It is to know the principle is conservation of momentum. Find the x components. Before, after, add them together, set them equal, solve problem. And that's what I did. Find the momentum in the x direction before, after, set them equal, solve problem. Same thing here. Know there's a principle of conservation of momentum in the y direction. Find out what they are and set them equal to each other. So in the y direction, I got 0. But in before the collision, but after the collision, I would say I have an m1 v2 final sine of theta minus m2. There's the minus 1. The y is going downward. Still getting ahead of myself. Okay, there. All right. So this is the y going up for the first one, and this is the y going down for the second one, and I would have a sine phi. Right? So again, in no way would I encourage you to memorize this equation or any of these very complex equations you're going to see either in the writing of the textbook itself or in working the solution manual. When you get to that solution manual, there's going to be some, you're going to look at that equation and go, whoa, that looks like a hard one. I better just memorize it for the test. No, not at all. Right? That's not the point. Not at all. The point is you can work this out from the get-go, and you need to look at the conditions for that case. You may or may not have conservation of momentum. You may or may not have elastic or inelastic collisions. You may or may not have two-dimensional collisions. You may or may not have the second one stationary or not. You may or may not have the first one stopping after. I mean, we had all those scenarios. And so we were not going to try to memorize all those different equations for all those different scenarios. We're going to know that momentum is conserved if there's no outside influence. We're going to also know that the energy is always conserved. And sometimes, under the special case called elastic, the kinetic energy is conserved. And if we know that much, we can write down any problem. And we can do every one in the back of the book. If I write down the third equation, it would look something like this. It would be 1/2 m1 v1 initial squared plus 0. That's the kinetic energy before the collision. And then after the collision, it's 1/2 m1 v1 final squared for the kinetic energy of the first one, and 1/2 m2 v2 final squared for the second one. Now notice on this one that there's no sine or cosine, right? There's no components to a scalar. Our energy was a scalar, so I don't have sines or cosines in that one.
Since they're colliding, will there be heat? Or that's when we skip the
Thank you. I guess I wanted to do the broad-based one. Plus heat. I still had the shuffleboards in mind, and shuffleboard is made of the hard materials. There's very little to no heat. So we often model the shuffleboard or the billiards, molecules, hockey pucks. They're all real hard stuff. And so their collisions are elastic. But we may not have that, right? These may be two deflated tennis balls that hit. And so there's heat created along the way. Maybe tennis ball is a bad example because that's going to imply rolling again. But yeah, you're right. But that would be the general case, and that's really what I wanted to put up here before we wrapped up today. And this really isn't the general case because I've already said this is a special case where the first object was stationary. And bottom line is, I cannot put all cases up here. That is not even the intent of my approach. The intent of my approach is to say, here is really where you want to get started. And so backtracking and marking in red, that and that are true if we have no outside influences. This is certainly always true if we include all of our forces and including the heat energy and the external ones there. But I guess it's these three that if I had a chance, and I guess I do, to give you another corny joke, do you want to know the answer to all the homework problems? There it is. Start there and finish. And I guess that's not completely true because we still have this issue of, well, what about outside influences? You'll see once you understand this, that's not going to be a hard one to answer. It's one that I'm not necessarily going to get a chance to answer today. As I keep saying, I'm waiting for Wednesday on that. I think we probably have just enough time to deal with a more complicated but fun problem involving collisions. It's kind of a little different than what we've been doing here for the basics. So for the basics, I've been saying, let's just take object 1, move it along, and hit object 2. But what if we change this a little bit? And as you saw earlier, one of these carts has a plunger. And so maybe with the plunger already kind of preloaded, maybe making them equal masses to begin with. Starting here, if I release the plunger, what would you say about the results? Using our conservation of momentum. Now let's see, I guess I would say that in this case, right now, they start off with no momentum. And is this a conservation of momentum problem? Is there any forces coming from the outside world? No. The plunger's certainly putting a force, if you call that number 2, onto number 1. And of course, Newton's third law then would say that number 1 is putting a force back on number 2. So next time somebody, or you accidentally hit somebody, remember, they hit you too, right? No, okay, all right. But there's an interaction here. And Newton's third law says they are equal and opposite. And it won't matter how big they are, and I should say not size-wise big, but mass-wise big. In this case, they're the same mass. So if they have no momentum before I release the plunger, how much do they have after? None. How do you get none momentum? They look like they're moving to me. Right, these are vectors. Don't forget that, right? And so one is going to the left and one is going to the right. And so the total momentum is still 0. Yeah. And in order for it to come out 0, doesn't it have to be equal amount of momentum to the left and equal momentum to the right? It does, right? Now in this case, the objects are actually the same mass, so what would I say about their speeds? They're the same, right? And so by releasing those, I would say these two objects have the same speed. Because of conservation of momentum, I can draw the conclusion that they are going to have the same speeds. What would change if I put a mass bar on here? How much momentum do they have before I release the plunger? 0. So what's the total momentum of the system after I release the plunger?
0.
Still 0. Does it matter that one is more massive than the other? No. Now, if we go further into this, then it does matter about the mass, because if they're going to have the same momentum but in opposite directions, so the total 0, what would you say about this one that has more mass? No. Must have a lower speed. In fact, it has twice as much mass, so what would you say about its speed? Half as much, right, exactly. So by releasing the plunger, you will see that that one does have a greater speed than that one, so that the two have the same amount of momentum but in opposite directions, so the total is 0. And you can even carry that one step further and saying, okay, what about now? Yeah, now that one should have 3 times the speed of that one, so that they have the same amount of momentum in equal and opposite directions, so the total is still 0 before I release it. Now the reason I brought all that one up is because, could you explain to me the propeller? How does the airplane move? How does the boat move? How does the propeller or prop move the boat or the airplane? In terms of Newton's laws, I'll start there, but let's move over to momentum in just a second. But in terms of momentum, Newton's laws, I would say the propeller puts a force on the air, so the air puts a force on the propeller. And just looking at this object by itself, I would say it has a force on it. It has a force from the air, and then that's what pushed it forward. But now looking at it as a system, moving into this chapter, looking at the cart and the air as the system, and saying, okay, right now I have in this room this big pocket of air. You can't really see it with your eyes, but there is a pocket of air right here. And I'll say it's not moving. There's probably a little bit of blowing around, but the doors are closed, windows are closed, the heater's not on, air conditioner's not on. Okay, so it's pretty stagnant air, not moving, cart's not moving. Total momentum is 0. So when I turn this on, what happens? Yeah, and just like the release of this plunger, the total momentum is still 0. What happens? Air goes that way. Cart goes that way. Or airplane or boat, whatever this happens to be. So something goes that way with the same momentum that goes that way. Does that mean they go the same speed? No. Same momentum. How about a rocket? Here's my rocket car. In fact, how would you describe maybe the motion and the movement of a propeller-driven airplane compared to a rocket or jet airplane? What makes this one go? And it's the same idea of this conservation of momentum. What would you say right now the momentum is between, I'll call these ball bearings my fuel, and my cart? 0. So if I create some mechanism that allows the objects, in this case the fuel, the heavy ball bearings, to go that way, then I will get an equal amount of momentum the other way. Not at all to say that they have the same speed, but definitely have the same momentum. So I was trying to save just this last bit of time to look at rocket propulsion. Here's a really good chance to ask ourselves, if I have a rocket that is filled with rocket fuel, how fast is it going after it burns up all of its fuel? Now, at first glance, this sounds like maybe I should do that with Newton's second law. I mean, it is asking for forces and acceleration. And maybe to keep it a simpler problem, let's just say, you know, as it is burning the fuel, kind of like this cart right here, they get the same speed, at least the same speed relative to the cart as they roll down. So maybe the first ball bearing comes over and is moving, say, 5 meters per second. But of course, once this starts moving at, let's just say, 1 meter per second, then the second ball bearing would come down and be leaving this at 5, at least relative to the cart. But isn't the cart really going 1 that way? So from your vantage point on the outside, I guess you would say this ball bearing is moving away with 4. It's 5 away from this one, but that one's moving 1 that way, so that's really a 4. You may even argue at some point this thing's going 5 meters per second, and so as the fuel exits at 5, and when I say 5, I mean 5 relative to the cart, it's really viewed as you as 0, not moving, because it cart's going this way and it rolls away from that one at 5, so it's from your vantage point not moving. Fair enough? And that's really how a rocket engine works here. You've got this combustion chamber. It burns these molecules, so they're not ball bearings. But if you think of those molecules as little tiny ball bearings, it gets them really hot and it shoots them out at the same speed. But I think what makes the rocket problem much more complicated is, what about the acceleration of the rocket? Does it stay the same? Yeah, many of you are shaking your heads. No, why not? The mass goes down. And in case you don't know much about rocket technology, it takes a lot of thrust and a lot of fuel. So unlike driving your car, where you could pretty much say your car weighs the same whether you have 20 gallons or 1 gallon in the tank, obviously your car is a little heavier with 20 gallons, right, than 1 gallon, but not much. But a rocket, very different. A rocket, something like 90% of its weight is fuel. And the other 10% or less is payload and other stuff. So can be a dramatic change in the weight of a rocket. So we have perfect recipe to solve that, hopefully, in the few seconds we have left here. So let's do this. Let's say that we have a rocket. And it's moving along. Let's just say it is already at some speed v. Well, let me use vi. We've been using vi. Has some initial velocity right now. Could be 0, so this could be the starting point of the rocket. And let me just do it sideways so I don't have to worry about gravity. I'm just kind of keep this simple in terms of the burning of the fuel. If we had the force of gravity, we'd have to add that into the mix. But in a few minutes, and just to see this in action, let's just keep it simple. Maybe it's just outer space, let's say. No gravity around. All right, so it's already got some initial speed, but let's put a little bit of fuel in here. This will be like one of those little tiny ball bearings. Let me call that dm. dm would be the mass of this little fuel. And you can see the calculus coming now. It's a little tiny amount. It's one molecule, let's say, going out the back. And of course, we're going to add up all these molecules. There's going to be billions and billions and billions of them every second coming out the tail end here. Okay? And so what will happen a moment later is this little piece of mass, dm, is now moving this way at some speed that I guess I would describe it as the speed it once had, initial, minus the speed, and your author uses the little sub e for exhaust. How quickly does it come out the back end? And then when I say how quickly out the back end, it is, of course, then that's, well, as measured by the person on the spaceship, that's why the total speed is the speed it has minus the exhaust speed. And of course, what that means here for the spaceship itself is that its mass, and so maybe I should come over here and call this m, has now been reduced. It is now an m minus a dm. And it is now going a new speed. It is going speed v initial, and it has increased by a small amount. Again, let me use some calculus here, dm. And so we are out of time. So let's solve this very quickly. I would say then that how much momentum did it have before? Well, before, I guess I would have m plus dm for the total mass of the ship times the initial speed. How much does it have after? Well, it should have the same momentum. It should be an m minus a dm times a v initial plus v here. And bummer, I didn't save myself quite enough time to do this justice. Oh shoot, I think I left something off here. That's the spaceship. Let me not forget the fuel. And so if I multiply all this out, and I better let you guys go, you got another class, ... And your author does a good job on all of this. He points out that when you write this out, and you're going to have you get this. And so he gets the change in speed of your rocket ship is the exhaust speed times the natural log of the initial over the final mass. And so maybe we'll revisit this on Wednesday, or maybe I'll just move on here. But it's a nice little problem getting to conservation of momentum as it flies along. And I do know you have a homework problem that in the past has really given students a hard time with the rocket, and so keep that in mind. Obviously, after the test, you want to come back and look at that as you do the homework. It's a tough rocket problem.